This is problem set 7 for Kevin Ahern's BB450 and BB550 class at Oregon State University, and also for the Biochemistry Free-for-All textbook. In this problem set, I take students through various scenarios relating to enzymatic reactions. In the first problem, it says, how is it that enzymes are able to catalyze reactions so much more rapidly than chemical catalysts? The answer to that question is actually a little complicated, but from the point of what we've learned about in the class, the enzymes have the ability to be flexible. They are able to twist, able to rotate, able to move, and that movement allows them to not only position things correctly, but allows them to bind molecules specifically and allows them to themselves be changed by the process of binding. We remember that Kochlin's induced fit says that not only does an enzyme change a substrate, but a substrate also transiently changes an enzyme. And that transient change of the enzyme can cause a stress or a strain that creates an environment where the catalytic process is much more likely to occur. That stress can be electronic, that stress can be physical, a variety of ways in which that can happen. But the point is that with an enzyme, the flexibility allows for many possibilities for catalysis that a chemical catalyst, which does not have flexibility, does not have. The second question says, what is the relationship between enzyme catalysis and equilibrium? And this is a very important thing for students to remember. As I noted in the class, an enzyme does not change the overall energy of a reaction. An enzyme simply changes the activation energy at which the reaction occurs. A molecule in an enzymatically catalyzed reaction starts at a certain energy level, and at the end of the reaction, the products have a different energy level. And those energy levels are set exactly the same whether it's an enzymatically catalyzed reaction or not. So the enzyme does not change the energy level, and since the energy level is related to the equilibrium, the enzyme does not change the equilibrium concentrations of reactants and products. So you might say, well, then the enzyme does nothing with respect to equilibrium, and that's not quite right either. The enzyme does a very important thing with respect to equilibrium. It speeds the rate at which a reaction gets to equilibrium. That's a very important consideration for an enzyme, because enzymes speed reactions and reactions move in the direction of an equilibrium. Therefore, the enzyme helps the reaction to get to equilibrium much faster. Problem 3 says, during the course of a reaction, an enzyme is changed, see the Kochlin induced fit, and such a phenomenon is not observed for a chemical catalyst. Therefore, is it appropriate to call an enzyme a catalyst? Why or why not? Well, the definition of a catalyst, of course, is that a catalyst is a molecule that speeds a reaction without itself being changed. An enzyme is speeding a reaction. And if it's transiently being changed, is it being changed? Well, the answer, of course, is that it's not being changed. That transient change that occurs during enzymatic catalysis is reversed or returned to the enzyme is returned to the original state at the end of the catalysis. So if we look at the state of the enzyme before catalysis and after catalysis, the state of the enzyme is exactly the same in both cases. So in that sense, the enzyme really does fit the definition of a catalyst. A scientist discovers a new enzyme mechanism that she calls rock, paper, scissors. This enzyme catalyzes an interconversion of 3 substrates and is related to the ping pong mechanism. And then I asked to draw how that might operate. Well, this requires not too much creativity to envision. It takes a little bit more to keep track of all the individual intermediates to do that. So let me attempt to do that. Let's imagine that we have the enzyme existing in 3 states. So in the ping pong state, the example I gave was that of transamination, where the enzyme either had a nitrogen or the enzyme had an oxygen, and it functioned to ferry that nitrogen or oxygen between molecules, either needing an oxygen or needing a nitrogen, etc. With rock, paper, scissors, we can imagine that the enzyme exists in 3 states. A rock state, that's an R, enzyme existing in a P state, and the enzyme existing in a scissors state. We can imagine that the enzyme existing in the rock state might interact with a molecule that is, let's say, a molecule that has an X on it that has a P, and the enzyme transfers its R to make a molecule now that has a structure Y that contains the R. In the process, the enzyme has picked up the P from the X and now has a P state. The second enzyme, or the second state of that enzyme in the process, could then interact with a molecule Z that has an S, and the Z could be converted to an A now that contains, in this case, a P. The enzyme in the process would gain an S. The third, and the enzyme in the S state, could then interact with a molecule B that contains the rock state shown here, and it could then go back and become molecule C, now that contains the S, and the enzyme would in turn flip back here. So that's one kind of a scenario that one could have for an enzyme existing in three possible states. Problem 5 says, it is said that the ordered binding of enzyme substrates for multiple substrate reactions is consistent with the Koshland-induced fit. And the question is why? Well, if we remember what happens with enzymes that bind multiple substrates, I described two common things besides the ping-pong mechanism that can happen. One is that we have what's called random binding of the substrates. And when random binding occurs, it means that the order in which the substrates bind doesn't matter. The reaction proceeds. So if I have a molecule or enzyme that catalyzes a reaction on A and B to make C and D, it doesn't matter if A binds first or B binds first. The reaction proceeds nonetheless. On the other hand, if I have an enzyme that has an ordered binding mode, then what happens with this enzyme is that it requires either A or B to bind first. So if we have a reaction that we put only B in and we don't put A, and we wait for the reaction to occur when we add A, the reaction will not occur simply by the binding of B. And what's happening in this case is that B is unable to bind to the enzyme until A has bound. Well, what does that tell us? It tells us, first of all, that the binding of A is somehow affecting the enzyme in a way that was different than the first scenario, the random scenario. In the case of the random scenario, it didn't matter. In this case, it matters because, most likely, the enzyme's binding state for B only properly forms after the enzyme has bound A into its appropriate binding site. Now, Koshland's induced fit says, of course, that an enzyme is affected by its substrate transiently. So we could imagine that in this case, the binding of A has affected the enzyme has changed its shape, and the change of that shape allowed for the binding of B. In the absence of A, B cannot bind. That means, therefore, that this is very strong evidence that there is a change or a flexibility that's happening in the enzyme, and it's induced by the binding of substrate. That's exactly what Koshland's induced fit is telling us, that the enzyme is changed by the substrate transiently. After the A and B react to make C plus D in this reaction, the enzyme goes back to the original state and has to again bind another A before the binding site for B will appear, because the enzyme is back to its original, the requirement for a catalyst, of course. Question 6 says, what are the units on the velocity of an enzymatic reaction? So it's important to remember that the units of velocity, the VO that's measured in the steady state conditions that we talk about in class, the velocity is equal to the concentration of product divided by time. So if we have that parameter, we have a reaction velocity that's equivalent or paralleled in some way by the velocity we think of with respect to movement. So the velocity of movement, of course, is the distance divided by the time. In this case of a VO for a reaction, we have the concentration of the product divided by the time. Question 7 says, a scientist is lazy a scientist is lazy and measures velocity of an enzymatic reaction after 10 minutes instead of after 1 minute. What effect would you predict this would have on the measured velocities? Well, if you remember my discussion in class about the pre-steady state and steady state conditions, I told you it was important for us to measure velocities early, but not too early. If we measure things immediately in the pre-steady state conditions, then we see wide variations in the concentration of enzyme and the enzyme substrate complex, and we might discover it was difficult to get reliable velocities because small changes in the time measurement of those might give us very big difference in apparent velocities. So in order to have consistent velocities, we measure velocities under Michaelis-Menten kinetics in what's called steady state conditions. In these conditions, the concentration of free enzyme and the concentration of enzyme substrate complex are relatively constant. Now, when this happens, we can rely more carefully on the velocities that we see. So what's the difference then between measuring a velocity at 1 minute versus measuring a velocity at 10 minutes? Well, you may remember that I said that we want to measure velocities early, and the reason we want to measure velocities early is if we wait too long, what will happen is product begins to accumulate. And as product accumulates, the reverse reaction will begin to become more prominent, and the reverse reaction will cause an apparent decrease in the formation of product. That is the forward reaction. Indeed, if we wait long enough, we will get at equilibrium, in which case the forward and reverse reaction rates will be the same. So we won't see any net production of products when we get to equilibrium. So we want to do our measures under Michaelis-Menten kinetics early enough that we don't have much product forming, and late enough that we're past the pre-steady state conditions. If you wait 10 minutes instead of 1 minute, you would expect that you would see a lowered velocity for the reasons that I've stated here. Question number 8 says, what is the difference between Vmax and Km? Now this is, on the surface, a very simple thing. We look at this and we say, well, between Vmax over 2 and Km. Vmax over 2, of course, is half of the maximum velocity. We can read that very easily off of the y-axis, and we remember that the units of velocity are concentration of product per second. So Vmax over 2 will be half of what that Vmax was that we measured. Km, on the other hand, is a substrate concentration. We measure it off of the y-axis, and specifically, it is the substrate concentration that gives a reaction of velocity of Vmax over 2. Km is not the same as Vmax over 2. We can't say that a gallon of gasoline, which was what powers a car, is equal to the 30 miles per hour. It would make no sense. But if we say that Km is Vmax over 2, that's really what we're saying. And that doesn't make any sense. A gallon of gasoline cannot be 30 miles per hour. A gallon of gasoline might cause a car to go 30 miles per hour, but it's not 30 miles per hour. Similarly, Km is not Vmax over 2. Question number 9 says, why haven't all enzymes evolved to be perfect? Now, I talked about this in class, but I'll give the answer here again. I defined the term, or the quotient of Kcat divided by Km, and I said this was a measure of the efficiency or the effectiveness of an enzyme. The higher that ratio was, the more efficient, the more effective the enzyme was, because a high Kcat means that the enzyme is catalyzing a reaction very rapidly, and a low Km means that it doesn't take much substrate concentration to get to Vmax over 2. So consequently, a high ratio means rapid reaction, very little substrate required. That's going to be the most efficient enzyme that you can see. I also talked in class about the fact that there are several enzymes that have a very high value of this, but all of these enzymes have a value range about the same. They don't go up above a certain point. And the reason that they don't go above a certain point is that the diffusion of the substrate into the active site of the enzyme becomes limiting. That's the slow part of the reaction for these incredibly efficient enzymes. So a perfect enzyme is an enzyme that has that maximal ratio of Kcat over Km. So why haven't all enzymes evolved to be perfect? The reason is that it would pose problems for controlling reactions in cells. As we will see, cells have to throttle. They have to control enzymatic reactions. Because if you have a foodstuff, let's say glycogen, which is a polymer of glucose to store glucose in our liver, for example, if that reaction is not controlled, the enzymes that break it down can break it down very rapidly. And the more rapidly they can break it down, the more likely they'll break down too much and cause problems. So if those enzymes had evolved to be perfect, the cell would have a very difficult time controlling them. So there's not an advantage to the cell to have only any more than a few enzymes perfect. Well, why do we have any enzymes perfect? Well, some enzymes are perfect because they're avoiding the production of unstable intermediates by moving very, very rapidly and taking very, very little substrate. They produce very, very little of, in some cases, a toxic intermediate. The toxic intermediate doesn't get a chance to form. There are other reasons that happen as well. But suffice it to say that cells do not have a good reason to evolve perfect enzymes for everything. Question number 10 says, why does the V0 versus S plot for an allosteric enzymatic reaction resemble the percent oxygen saturation versus oxygen concentration for hemoglobin? And again, this is another one that I talked about in class. But the answer to the question is that they both involve binding. We're measuring binding in the case of oxygen and hemoglobin. We're measuring a reaction in the case of the enzyme. But since the reaction is completely dependent upon the binding of the substrate, the reaction velocity will mimic the binding effect of the substrate on the enzyme. So even though hemoglobin is not an enzyme, it does bind a molecule, in this case oxygen, just like an enzyme binds a substrate. And since the binding of the substrate is closely related to the reaction of the enzyme, the binding behavior of hemoglobin mimics the reaction behavior of an enzyme. Question 11 says, why is Vmax dependent on the quantity of enzyme, but Kcat is not? Well, Vmax is dependent upon the quantity of enzyme used. This is very easily experimentally determined. If you take a given enzyme and you do a series of reactions all using the same amount of enzyme and varying amounts of substrate, you can produce a V versus S plot that looks something like this. And if you take that same reaction and you double the amount of enzyme, what you will see is you will get something that looks like this. I've tried to draw that so that it's about twice as much. So the Vmax that occurs for a reaction depends totally upon the amount of enzyme that we use. So we say, okay, well, I can buy that. Why then is it the case that Kcat is independent of the amount of enzyme? And the reason is because of the way that Kcat is calculated. Kcat is calculated as the Vmax of a reaction divided by the concentration of enzyme. Remember that Vmax is a concentration. That is, the velocity is a concentration divided by time. So we have concentration of product divided by time divided by concentration of enzyme. Well, both of these concentrations cancel out. And it doesn't matter that we have product concentration or enzyme concentration. They both cancel out so that the units that we get on Kcat are equal to per time. Now you might say, I don't believe that. I say, okay, well, let's look at what's happening in this reaction. Imagine I told you that I doubled the amount of enzyme. If I doubled the amount of enzyme, what was going to happen to the Vmax? The Vmax was going to double. And you can see pretty quickly what happens. Cancel, cancel, and I have exactly the same thing. So the concentrations cancel each other out, and we're left with units of per time. 1,000 per time, which would be a value for a Kcat for an enzyme, for example, could be 1,000 per second, could be 1,000 per minute, depends on how we've measured the thing, but let's say it's 1,000 per second. That 1,000 per second corresponds to the production of 1,000 molecules of product per 1 molecule of enzyme per time. And that's what Kcat is. The last question says you were studying an enzyme inhibitor, and notice that the Vmax you observe in the presence of an inhibitor is equal to the Vmax for an uninhibited reaction using only 80% of the enzyme. What type of inhibition is this? So let's draw out what I've just described. Let's imagine that I have a plot now of V versus concentration of S, and I say that I'm doing a reaction where I have, let's first of all draw it as if we have no inhibitor. So here's the V versus S for no inhibitor. And let's say I do the same reaction without an inhibitor, and I only use 80% of the enzyme. So we'll say 100% enzyme. Okay? And I do the same reaction in the presence of only 80% of the enzyme, and I see something like this. Now, if I take and I do the reaction with an inhibitor, I get, and I'm going to use a little squiggle here to indicate with the inhibitor, I get exactly the same line. Now, what's going on? Well, what's going on here is it's telling us that the inhibitor has caused the Vmax of the reaction to be decreased. And we know from the different types of inhibition that I've talked about that the only type of inhibition that decreases Vmax is non-competitive inhibition. Competitive inhibition, competitively inhibited reactions, have exactly the same Vmax as uninhibited reactions. So this must be, based on what we've talked about in class, this must be a non-competitively inhibited reaction. So we have a non-competitive inhibitor. I've drawn here a V0 versus concentration of S plot, and now I'll draw a Lineweaver-Burk plot for both of these. So now we're going to plot a Lineweaver-Burk where we have 1 over V versus 1 over S, 1 over the concentration of S. And we know from the data from the V versus S plot that a Lineweaver-Burk plot will have a straight line for the uninhibited reaction looking like this, where this value is 1 over Vmax, and this value is minus 1 over Km. Now for the uninhibited reaction, for the inhibited reaction, we know that non-competitive inhibition has Vmax decreased, Km is the same. So we know then that one of the points of the inhibited reaction is going to be right there. It's going to be the same for both because the Km is unchanged. We also know that if the Vmax for the inhibited reaction decreases, that 1 over Vmax will actually increase, and so we could expect to see a point something like there. Then, knowing 2 points, we could say, and that's supposed to be a straight line, we could say that the inhibited reaction, okay, non-competitive inhibition, looks like that, and the uninhibited reaction looks like that. And we would have answered the question.